Morning. The today's experiment is on performance characteristics of the synchronous motor. Here we are drawing V and inverted V type of curves for the synchronous motor by observing its performance under no load condition and full load condition. And let us see that first nameplate details of this machine. The power rating is 3 kilowatt and speed is 1500 rpm. The armature current rating is 4.5 amperes. Input supply voltage is 415 volts. Excitation is 40 volts, and it is a 3-phase machine running on 50 Hz supply. So let us come to the title of this experiment. It is V and inverted V curves of the synchronous motor. These V and inverted V curves are performance characteristics of the synchronous motor. The operators required are voltmeter of 0 to 600 volts, ammeter of 0 to 5 amperes. Here in place of wattmeter, I replaced here a power factor meter. So here we need a power factor meter. So that is this power factor meter. I already replaced in this circuit setup. Now let us come to its circuit diagram. So this circuit diagram consists of one 3-phase variac for varying input voltage. This is 3-phase supply is fed to the 3-phase variac, and from 3-phase variac the supply is given to the stator of the synchronous motor. This part is called as the stator of the synchronous motor. Next part is the rotor of the synchronous motor. Here a rotor of the synchronous motor is also excited with some excitation called a DC supply. So for this DC excitation we need to measure the field current, how much we are supplying to the rotor, and similarly here we will measure the armature current, how much we are supplying to the stator. So mainly we need to have the readings of armature current, field current, as well as the power factor. Here this is one wattmeter, this is another wattmeter connected between the two lines. So instead of these two lines wattmeter, I have a 3-phase power factor meter. So this will give the direct measure of the power factor. So here we are using in this test the wattmeters to calculate the power factor. So instead of these two wattmeters, I replaced this one. And this test has been conducted for the two loading tests. First one is a no load test. We are running the machine at rated speed, means it's a freely running condition. We are testing the machine. We are taking the readings of armature current and field current and the power factor, but different field current, different excitations. Now the same procedure is repeated for the loading condition, means that the machine is now loaded by means of some external means. Here brake drum is used across the rotor to control its speed. So that here I am putting some additional weights on the rotor to adjust its speed, so that some load is indirectly applied on that. I am assuming that as a load test. That load test again I am taking the readings for what the variation of field current with the armature current and the power factor. Let us come to the readings that we need to have for this test. So this is a regular table. I replace these wattmeters, wattmeter 1, wattmeter 2, and that is total power by the summation of this. So from that we are calculating power factor. Instead of this entire procedure, I just modified, like I replacing this power factor meter, so that directly we can get the power factor here. So I'm only taking only 4 readings here. Voltage, this is input supply voltage. Field current, this is from the DC excitation to the rotor. This is armature current, this is a load current also we can assume, and this is the power factor, load power factor under the two variations, one is the leading and lagging. Then this is under no load we are taking some readings, under full load we are taking some readings. From the existing readings of this test, we will plot the curves like the variation of armature current with the variation of field current. So the variation of these two parameters is giving a performance curve for the synchronous motor. Like this shape seems to be a V shape, so that we are calling it is a V curve. So this is for no load test. Similarly for full load test also we can have one more V curve. And another one, we can draw the performance curve for this test. that is variation of power factor to the field current. So here the performance curve of the synchronous motor with the variation of power factor and field current is seems like a inverted V. This is the reverse V. So that we are calling it is a inverted V curve. This is plotted for no load, and we have one more curve here is for full load. So finally we need to plot these two characteristics from this test. So this test is saying that type of operation means that a machine can be able to operate under two different conditions. One is lagging load condition, another one leading load conditions. So that the synchronous motor can be operate for any excitation, for this is a below excitation or above the excitation. So that we can obtain from these two curves, that we can conclude from these two curves. So let us come to the experiment. So this experiment setup is connected. So we have totally 4 meters here. One is voltmeter. We have 2 ammeters. One is connected in stator of this synchronous motor, that is we calling as a load current, and another one is we have on rotor of a synchronous motor, we have it as a field current, and one more meter. This is a 3-phase power factor meter. Here we have 2 types of power factors to be measured on this. That is, one is on leading scale, another one is on lagging scale. So the variation, whatever it may be, we are getting, either you can take the lagging as a plus and the leading as a minus. So in that way you can take the readings, and while you're plotting the characteristic curve, you can say that so leading is on negative scale and lagging on positive scale. We can plot the curves. So let us start the experiment. So coming to the procedure of the experiment, first of all we need to apply its rated voltage 415 volts to the test setup. So once you apply the 415 volts to the test setup, then we need to adjust the field current. So we need to give the field excitation by means of some DC excitation, so that the variation of field current will brought the variation in the power factor also. So these two variations will observe along with this variation of armature current. So how to vary the input voltage? In the sense we are using a 3-phase variac here. By adjusting this 3-phase variac slowly, gradually, I am increasing the voltage around 415 volts on this. So later this is the DC excitation setup. So this is connected to the machine, and once I excite the DC supply to the rotor, then the field current variation will observe. So we will finally take variation of field current with the armature current as well as the power factor, and 2 different loadings. Now I kept the machine on free running, so that it is not at all running now. If I give the supply, I am varying gradually. So I set up here as a 415 volts as a voltage by varying the 3-phase variac. Now the machine is now at its rated speed. It is running at its rated speed. So the machine is under free running. So this loads are removed. So this we have to treat it as a load, no load condition. So once it is done, so we need to observe. So the voltage, what is the voltage here, and what is the current, armature current here, and later the power factor. So now at this stage the field current is 0 because I have not given any excitation. So the field current is 0. This is at the starting step of the machine. So if I want to adjust, because I need the variation of field current with the armature current, variation of field current with the power factor. So definitely I need some field current, otherwise I cannot able to plot the characteristics. So that for that what I am doing is, I am giving the field current, means that I am adjusting this to this side so that the exciter will be started. Now the excitation will be applied there. So once the excitation is applying slowly, in steps I am applying the excitation here. So you can see that variation of current. So different variations of current we can have here, and I am noting these values now. Suppose this field current is at 0.8. First reading I am taking is 0.8, and voltage I applied is 415 volts, and now at this time my power factor is around 0.95 lagging, and after that the current armature current is around 1.5, so that I am taking that 1.5 amperes here. So this is for first reading I am taking, because I adjusted the field current so that the variation is observed in both power factor and armature current. Now in second step I am observing the field current. Here it's I varied somewhat the DC excitation. This is lead to now 1.3. So the field current value is 1.3 amperes now. So for that we have 0.98 is leading power factor I am observing here. And for that we have current reading is armature current 0.5 amperes. The 415 volts will be remain same supply voltage. I didn't varied any supply voltage, so that it remains constant. So now for the next excitation I have here the field current is now 2 amperes around. At this stage, about my value of power factor is the unity power factor, so the UPF. So this is also around 0.5 415 volts. So that the next third step I am taking the values of current here. So next another excitation I am providing. So next here we have a 2.9 amperes of current in the field, and proportionally we have 0.98 lagging power factor. Now it is shifted onto the lagging scale. Previously on leading scale, now it is shifted onto the lagging scale. This is a 0.98 lagging now. So the current, if I see in that, now your armature current started increases because your power factor becomes leading to lagging, so that the armature current started increases. This is 0.6 amperes it seems, 415 volts. Next another reading I will take. Stop. Next here same 415 volts. This current is around 4 amperes, and my power factor is 0.96 lagging, and it's around 2 amperes of armature current is there.